Hi everyone. So today's topic would be test points, and we would be definitely looking on to why test points are required or how do they look like. But prior to that, I want to spend some time on how are we testing a fault in DFT, right? Because that would help with the understanding of why test points are required and how do they work. So let's consider this sock, and this has three scan flops which are stitched with a blue dotted line in the below fashion. Right. So in order to test a fault on the combinational logic that is lying within this combinational cloud, there is a requirement to load the scan flops with a deterministic value. So to load the scan flops in a deterministic value, I perform a shift operation in which the scan enable is kept to 1 so as to choose the SI path, and at the sock level this port is being driven by the AT. So AT drives the deterministic data, and then because scan enable was 1, the SI path is selected and all the scan flops are loaded with a deterministic value. Let's say we loaded this flop with 1, this scan flop with 0, this again scan flop with 1. So now, as soon as our shift procedure is completed, we bring the scan enable down, and eventually we are entering into the capture phase. So in the capture phase, the mux within the scan flop is being driven by the D leg. So at the end of the shift, 1 would have reached here, 0 would have reached here, and this stimuli would have made the combinational elements within this cloud to toggle and eventually get some output as alpha. The output of this combinational cloud gets captured through the D leg in this flop, and we again perform a shift out operation to compare these captured responses on AT. So this would be having some D cone as well, right? This would have captured some value as well. So when the after the capture, we again perform a shift. We make the scan enable 1, and then we are shifting out the captured responses and comparing it with the expected values on the AT. This is how we perform the basic test operation in DFT. Right? Now we would be moving on to the test points, or what is the basic intuition behind it, right? Now let's say we have a OR gate with us, and I wanted to test a stuck at 1 fault here on the A leg. So the general notion would be drive the A leg with 0 and the B leg with 0, and if the output is 0, that means the circuit is fault free. But if I received a value 1, that means this OR gate has some structural defect associated with it, right? Taking this as a baseline, now again I have to test the stuck at 1 fault on the A leg of this blue OR gate. Going by the same analogy, I would at the end of shift I would load the scan flop with 0, this scan flop with 0, and at the output of the OR gate, 0 is the fault free value and 1 is the faulty value. But the issue arises here is that the output of this OR gate is driving a AND gate whose another leg is tied to 0. So whatever value we count or we get from the OR gate, that get masked at the AND gate level. This flop would always capture a value 0. So technically, even if I excited this fault here, I received some output here. Because this response was not able to reach a scan element, I won't be able to test this OR gate. I would take you in simpler words. I pushed in 0 here, I pushed in 0 here as well. Let's say the circuit was faulty. So because it was faulty, I got a 1 here, right? I got a 1 here, but because there was an AND gate whose another leg was 0, it masked the faulty value and I got 0. Technically, I am not able to get the coverage for this logic because it is being masked right here. So now we are stuck because the logic was like this. We are not able to test the OR gate. There is a requirement to introduce something so that we can get the coverage of it, right? So there comes a way. What if I take a fan out from here and take that fan out from here and observe that into a flop, right? Let's call this as observation test point. Let's say the chain was stitched like this. Okay. I add another flop in the design whose D input is coming from this node and right, this becomes a part of the chain, right? So eventually this was not a functional design flop. I added another flop which was observing the output of the OR gate and I stitched that into the chain. That's why I can shift out the captured or the observed value of the output of the OR gate. This is called an observation point. And similarly, if I could do something to control the node here, which is tacking to 0, which is always tied to 0, then if I could do some logic, let's say there I introduce a OR gate here, which is driven by another scan flop, and this scan flop can be loaded at the end of shift with some value. Let's say I bring 1 at the end of the shift, this would make this output as 1 and this path gets transparent, right? So you have the option to choose from a test point which is a control point, or you can add an observation point to get a coverage. We would in the next video we would be following on to the structure of the test point and observation point, but this is the intuition behind it. I mean, this is why and how why test points are required and how they solve the coverage problem. Thank you.